There are many examples in our daily life where friction can be used to our advantage, and a very special case, which I will discuss with you now, is often used by sailors by holding, controlling a very massive object, a very large force, controlling it with a very small one. And you do that by making use of friction. You wrap a rope around a pole or around a rod, and you use the friction between the rope and that rod to your advantage. And it works as follows. Here is this rod. It doesn't have to be horizontal as this one. And I hang on this side of the rod, I hang with a string, a very massive object. Capital M. So the tension here, T2, would be mg, assuming that it is not accelerated, that it is at rest. I wrap this rope around here several times, and here I hang an object which is substantially less in mass, which is m, little m, and the tension equals mg. If there is no friction at all in this bar, then, and the rope is near massless, then T1 will be the same as T2, so the situation will start to accelerate. However, if we make use of the friction, then we can have a stable situation, we can have static equilibrium, so that this one is not moving and this one is not moving, and then we can have T2 to be way, way larger than T1 by using friction to our advantage. Let's blow up that center portion, radius r, and let us have this rope here. I'll give the rope a color. Doesn't have to come off vertically, of course. Could be at any angle. There it is. And so here is my T1, and here is my T2. And we take the situation that the pull on this side is way larger than on that side, so that this rope wants to slip in this direction. That's what it would like to do. If you look at these small little sections of the rope, it is immediately obvious if the rope wants to slide in this direction, wants to start slipping, that the frictional forces in these little pieces here are all in this direction. All the way around. And therefore, it helps T1, so to speak. And so, because of the friction, which is opposing T2, T2 can now become much larger than T1. What you have to do to calculate this analytically, you have to evaluate these individual frictional forces for these very small slices, so that becomes an integral, and then you have to integrate it over an angle which I will call theta 0. And I remember when I last lectured 801, that was in 1993, I derived that in class, the relation between T2 and T1 as a function of this angle, theta. And that took me about 5 minutes, and after 5 minutes, half the students were asleep. Now, I'm not sure whether you want to sleep 5 minutes, but I don't think, frankly, that you deserve it. So I decided to not do the derivation, but to refer you to the book, which is page 361. And you will find then that in the situation that the rope wants to start slipping in this direction, that T2 divided by T1 is e to the power mu times theta 0. If the friction coefficient here is mu, it would be the static friction coefficient. So that is the result. And notice that it is independent of the radius of this bar, which is not so obvious, funny, strangely enough. Whether the bar is this small or this small makes no difference. It only depends on this angle. This angle could be very large. You could wrap it around 10 times, as we will do very shortly. So there's no restriction on theta. If there were no friction at all, notice, then at the moment that it starts to slip, e to the power 0 is 1. That's when t2 equals t1. That's obvious. So you can't play this game if mu is 0. You need friction. That is at the heart of this whole problem. And so now let's put in some numbers so that we get an idea of what we gain. So let us take a situation that we take, let's say, 3 turns. We wrap the rope around 3 times. So 3 turns. That means theta 0 equals 6 pi. And that the friction coefficient mu be 1/5, 0.2. So e to the power mu times theta 0 is now about 40. So what that means is that with a force on this side, which is 40 times smaller than a force on that side, I have a balanced situation. I can hold this in my hand and counter, if you want to think of it that way, a force on this side, which is 40 times larger. But if I take 6 turns, then e to the power mu theta 0 will be about 2,000. 2,000. So now I can really control an elephant. Imagine now that I have here an object, capital M, which would be 5,000 kilograms. Make it 10,000 kilograms. That's what I'm hanging here. I can hang here now a mass which is 2,000 times less massive. That means I could hang there 5 kilograms. And the tension here would be 2,000 times less than the tension there. The system would be about to start slipping, but it's not slipping. There is complete balance. So imagine I hold this part in my hand. Here is this 10,000 kilogram weight, and I hold this in my hand. All I need is a force of about 50 Newton, and I'm standing there, and on the other side is this 10,000 kilogram weight. And now I just make my force a little less than 50 newtons. And what will happen now, it will start to slip. Remember, because we calculated here the requirement for just not slipping. So now I let it go, and then the 10,000 kilogram on the other side will slowly go down. I can just control it, and I can stop it, and I can control it with a very, very small force. Now comes a question for you. Suppose I wanted to raise that 10,000 kilogram. Could I now pull a little bit more than 50 newtons? Just a teeny weeny little bit more. Would then that 10,000 kilogram come up? I see people shake their heads. Who thinks it would come up? Who thinks no way? Who doesn't think at all? Most of the people. All right. Sorry, I didn't mean to be nasty. There's no way that you could pull it up. Because if you want to pull this up, the situation completely reverses. Those frictional forces for this rope to go in this direction will flip over. In other words, what is now T1 in our calculations will become T2. So if you want this side to go down, if you want to have it slip in this direction, you're going to have that T1 divided by T2 is now e to the power mu theta 0. And so now if you have 10,000 kilograms here, and if you had 6 turns, then the force that you need here is 2,000 times larger than 10,000 kilograms. And so you would need 20 million kilograms. So it would be the dumbest thing to do to lift it. You don't want to lift it. You use this device only to balance a very strong force. That's the way it's used by sailors, and even to control it, because you can slowly release it, and then the force on the other side will start to move. But you cannot use it to lift something. I have here a plastic bin, and in this plastic bin are 4 of these 15 pounds lead bricks. Would you do me a favor and come up here and convince yourself that 3 are already in there. I don't want to put them all 4 in, so I decided I'm only going to put the last one in. You see those 3? Thank you very much. And I'm going to put the last one in. It's very heavy. You want to check this, by the way? This is careful. It's very, very heavy. Yeah. Okay. Okay. 15 pounds apiece. 60 pounds we have up there. And now I'm going to wrap this around this bar, which is your bar. The radius doesn't matter. And why don't we start with 6 rotations? 1, 2, 3, oh my goodness, 4, 5, 6. Okay. Now I'm going to lower this platform that we have, that is holding it up. I can lower it. And it will shortly be hanging now on my rope. There it is. I can remove this now. We don't need this anymore. And we don't need this anymore. Effortless. 30 kilograms. Hardly any force. Very gentle. Now let me lower it a little. There it goes. Just lower it. Would be nice if I had to do even less. Let's put a few more turns on. 1, 2, 3. You know what we could do? We could put so many turns on that the weight of the rope itself is enough to balance it. Let's try it. Not yet. Put a few more on. 1, 2, 3, 4. We have 12 windings now. And the rope, the weight of the rope is now sufficient to balance the 30 kilograms. So you see this in action now. This is a marvel. Well, let me put a few more on because I don't want it to come down during the lecture. I want to be sure that it stays there. And we're going to secure it here. So you see how you can use friction to your advantage and get an enormous gain by factors of thousands and more. And this is used quite frequently.